An important part of machine learning is what's called model selection. But one thing which is a little bit can be confusing about this is that when people say model in this context, when they say model, they don't mean model in the sense of choosing from a different type of model, like if you were doing classification, choosing between k-nearest neighbors and naive Bayes or trees or SVMs or those types of models. What they mean is choosing between different complexity levels. So it's maybe a more appropriate name would be complexity selection. And here, what do I mean by complexity? Roughly speaking, when I say complexity in this context, or when people talk about complexity in this context, they mean, and this is not a formal definition, but they mean the flexibility of the model to fit or explain different types of data, different sets of data that you may get. So this is the complexity or the model complexity. And model selection is choosing from within a class of models, choosing an appropriate level of choosing an appropriate level of complexity for your data. So let's look at a concrete example to see what do I mean by this. I think an example that probably everyone is familiar with is linear regression using the maximum likelihood estimate and what's the maximum likelihood estimate for the parameter vector W. And so in linear regression we're choosing some function f. So f of x is the dot product of our parameter vector W with some basis functions, with some vector of basis functions phi of x. And let's take x here to just be real valued. And let's take these basis functions. This is the usual example that people use. People usually use a polynomial basis for this kind of simple example. So what is the polynomial basis? Well, the polynomial basis is the kth coordinate of this phi vector, phi sub k of x, is just x to the k. So x is real valued, we just take x to the k, and we'll take, let's put it over here. We take this phi vector, the first coordinate is phi 0, then phi 1, phi 2, up to phi, let's say b for basis. And then I think everyone's probably seen the picture. Let me draw a nice big, if I can draw a straight line. Not very well, apparently. Let's make a little more room. Draw a nice big axis here. So I think everyone's probably seen the picture. Let's say we have some data. Let's say maybe we've got a point here and a point here, something like this, and I'll draw it sort of very suggestively to indicate a cubic. So if we had this data, and let's suppose, well, maybe we'll come back to that. So we say this is our data that we get, where this is x and this is y, or f. Well, it's not f of x. Excuse me. F of x is going to be our prediction function. And then let's think about what happens if we do the MLE. We choose the MLE for W, and different values of this b. So b here, let's say when b is small. Let's think about b is 1. What are we going to get? Well, it's going to be a line, right? Or it's going to be like some affine set here, some line, something like that maybe. So this is b equals 1. And what if b equals, let's skip 2. Let's go ahead and we'll jump to 3. 3 would be probably a good one. So 3. So when b is 3, we get the constant. We get 1, we get x squared, and we get x cubed. So we can do a nice cubic there. And now let's say, and that was, I should have written, so that was b equals 3. And now what happens if what if b is big? What if b is just like 20? Well, when b is 20, actually we might not even have 20 data points, but so when b is big, oh, let's try to make it at least a function. This is going to be some crazy thing. It's going to like try to go through every single point. It's just going to be all over the place, something like that. And I think it seems fairly clear that this is just crazy. This is just way overfitting the data, right? I think everyone's probably seen this picture before, where when you choose your basis functions, when you have too many bases, when your polynomials are too big, then you can just overfit this thing when you use the maximum likelihood estimate. So here, this b, this b number, the number of basis, well, it's the number of basis functions plus 1, I guess, or minus 1. This is a complexity controlling parameter for this model, right? Because when b is small, like 1, then the complexity was very low. It had very little flexibility to fit the data. It was not very flexible. It could just draw these lines. But when b was big, when b was like this 20, right? This was b equals 20. It was super flexible. It was just way too flexible, and it could just go through. I mean, it might, in this case, 20 might even be able to go through every single point. I think it probably could. I don't think I drew 20 points. So b could go through, when b was 20, the prediction function, f of x, could go through it could just overfit the data. So it had too much flexibility to fit the data. And when b was 3, it was sort of just about right. So this is an example that I think probably everyone's seen. And so hopefully this gives you, as a first example, gives you a way to start thinking about this. And now you may say, let's think about another example. Now you may say, oh, okay, well, that's just, you were using the MLE, and the MLE we know can overfit. But what if we did, I know how to fix that. We can do Bayesian linear regression, or we could take the map. So we could either do Bayesian or use the map, use a maximum a posteriori estimate for W. And when you do this, of course, you put some prior on W, and typically you may put a zero mean, a normal prior with zero mean, and some spherical, some covariance function that was just a diagonal matrix with constant, the same variance in each coordinate. And so, but you have to choose this sigma squared, right? You have to choose sigma squared. And so not only in this case do you have to choose b, you have to choose the number of basis functions. You have b and sigma squared. B and sigma squared are complexity, well, I won't write it again. B and sigma squared are complexity controlling parameters for this model. Now, why is sigma squared a complexity controlling parameter? Well, so if we look back to our drawing here, let's think about what happened. When b was large, when b was 20, like here, why did this happen? Why did this function go crazy? Well, what was happening was that the MLE for W, remember W is a vector. Of course, I'm sure you know that. W is a vector. It goes from W0 up to WB, because we're taking the inner product of W with phi. So W is a vector, and what was happening in the MLE when B was 20, or when B was large, is that some of these coordinates in W were getting jacked up to, really big values, big positive values or big negative values, and that's why this thing was going crazy. So what happens when you put this kind of prior on W in both of these cases, is that you're favoring functions for which W is small. The coordinates of W are small. And so as a result, the functions that you're going to get are going to be more, they're going to be more smooth and flat. They're going to be more like, even if b was 20, it might be a more smooth or sort of flat function. Something like that. Might be a little wiggly, but not too bad. Something like that. So this is a complexity controlling parameter, because if you set it very small, then everything's gonna be like a flat, very smooth function. And if you set it really, really big, or too big at least, if you set sigma squared to be too big, then you're just essentially back in the case of maximum likelihood, that this prior is basically having no effect. So you need to choose an appropriate value of sigma squared in order for this to work appropriately. Now those were a couple of regression examples. Let's also look at a classification example. So we saw this one, b was the complexity parameter, the number of basis functions. Here we had b and sigma squared. And now let's think about k nearest neighbor classification. Make a little space here. Well, in k nearest neighbor, you have to choose the parameter k. That's essentially the only parameter. You also have to choose the distance metric that you use, or dissimilarity function that you use. But the complexity controlling parameter here, or at least, I mean, it depends on, I guess, what dissimilarity function you choose. But you always have this complexity controlling parameter k in k nearest neighbors. So let's think about that one. So here k, let me put in purple to be consistent. K is a complexity controlling parameter. And why is that? Well, let's think about the picture for k nearest neighbor. We've got some data. Maybe we've got some, let's make it colored. Maybe we've got some red data, something like this. And maybe we've got some blue data, some positive examples and some negative examples. And when you do k nearest neighbor, when k is 1, let's say if k is 1, then you're going to get the Voronoi, or how, I don't know how, I guess I can't pronounce that word, Voronoi diagram, somebody's name. It's going to go something like this. It's going to give you this sort of boundary. And this is all sort of jagged. And if we had lots more data, then this would be super, super jagged. So this would be k equals 1. But when k is big, if k was like 5 or something, or and this is going to be it won't be smooth. I can't say smooth, but it's going to be more straight. It's not going to be so jagged. I haven't calculated this, but when k is bigger, then you're going to get a decision boundary. I'm drawing the decision boundary here. The decision boundary is not going to be quite so jagged and wiggly as it was in the k equals 1 case. So this is a complexity controlling parameter, right? Because when k is small, when k is 1, then you can fit everything. You can classify all these, I mean, you can get this decision boundary that's just very complicated. But when k is large, then you have these more sort of smooth decision boundaries. So you need to choose an appropriate value of k. Alright, so those were just a few examples of the complexity controlling parameters that you have to choose when you're doing model selection.